Okay, awesome. Welcome. I'm so glad so many of you here, and I'm so glad there's actually real diversity in the room as well. So awesome. So the talk is called The Anatomy of an Exploit, and it's me trying to introduce exploitation to programmers, C++ programmers in this case. My name is Patricia Aas. I'm a trainer and a consultant currently for my own company. But throughout my career as a C++ programmer, I've been working on browsers and in embedded. And I even had a small stint as a Java consultant for a couple of years. I come from computer science. I have a computer science degree. And so I found trying to learn exploitation to be very weird for my mind, because it is a lot based on myth, a lot of storytelling, very unstructured kind of discipline. And so I was really happy when I found a couple of talks by a guy called Halvard Flake and another guy called Sergey, who tried, and both of them are mathematicians by background, trying to formalize this in some kind of formalized model and actually writing papers trying to explain exploitation. So I'm going to use that as a background for this talk. So they talk about something called the weird machine. And so in the weird machine, the model includes the idea that the program, the target program, the one that you want to exploit, is based on a programmer's mental model of how it's supposed to work. And the mental model has certain states, and you transition from a state to another, and it is all of the states that are intended by the programmer. So, so these are the two people this is based on. So the idea that if you have some kind of vulnerability that is triggered in program, then you enter into an unintended state. And they call this unintended state a weird state. So in this weird state, you can maybe have memory corruption or some UB triggered fanciness that made, so you're now in a state that was never actually intended to be in by the programmer. So this is a whole other set of states. The idea is that you want to be able to control these weird states, control the transition between one weird state to another weird state. This is very hard because weird states are usually very unstable. They cause crashes. They cause memory corruption. They are inherently very unstable. So the art form is to be able to control flow after you've kind of exited the program as it was intended into this weirdness. And what you see is that these map to each other. So this weird state was the state that was entered because you maybe had some memory corruption, or you deleted a pointer, but the pointer is going to be used. So you're going to have a use after free. But what you see is that the transitions in the normal code from a sane state to another sane state will trigger transitions in the weird machine as well to other weird states. So for example, you had somebody use this pointer, so now you have a use after free. And this causes you to be in another weird state. So we're going to get back to this, but the idea is that at some point maybe you can control this weird machine enough to be able to execute your own code in there to do what you want to do. So we'll get back to this model a little bit later. What I've found very strange as a programmer looking at exploitation is because I'm used to being able to modify the program. If the program has a bug, I can change the program, recompile it, and run it again. But from an exploitation point of view, the program is fixed. It is compiled. It is done. There is no changing it. And so trying to look at binaries as objects to manipulate was a little bit of a mind shift for me. And it has to do with the fact that you are injecting your behavior in this binary through data that enters this binary. And that could be from user input, it could be from network traffic, it could be configuration files that this program will read from disk, it can be even environment variables that are loaded into memory. Somehow you want your external input, which will be your program, injected into the memory of this process. So things that usually are utilities, like memory, loaders, memory allocators, linkers, the heap, and the stack, instead become data structures that you're manipulating to run your program. And your program is programming the weird machine, some kind of very strange specialized machine around the program, which is fixed. And so you will see a lot of exploit developers will specialize in certain types of programs or specific programs. So you will have exploit developers who are specialized on Acrobat Reader, for example. Because Acrobat Reader defines an architecture for them, an architecture of a weird machine that they program. And so whenever there is an update to Acrobat Reader, their weird machine might break because something was fixed or something was moved. So it's a different way of thinking. So exploit development is programming. It's just programming of this very weird machine. So we're going to play around with the small program, the whole presentation, and I'm going to show you, as I'm showing you, the ways that we're going to try to do the baby steps in exploiting this program. I'm also going to show you how a lot of things have changed over the years. So we are looking at, so we're going to be turning stuff off and making things then easier to exploit. And the reason why I want to do that is I want to make it clear that oftentimes if you find an error, like you upgrade your compiler and then you suddenly have an error, then you Google the error, you are on Stack Overflow, and the first answer on Stack Overflow says, oh yeah, but you can turn that off. Just copy paste this into your CMake file or just run this command on the box and you can turn this problem off. So the idea here is to say that sometimes those turning off things actually have real consequences. Okay, so the first thing we're going to look at is inherently dangerous function. This is a name of a common vulnerability enumeration. It's number 242, and it's called inherently dangerous function. And it's basically, the whole item is basically around a function called gets. So gets takes some input from standard in and writes it to this buffer. And so the first part of this talk is going to be about these two lines of code, basically. But we'll put them in context. So here they are. So this program I borrowed from Olve Melda, and because I thought it was kind of fun and it fits on a slide. So it's a C program. It has 3 functions. It has a main here at the bottom, which basically just prints some text and then calls this middle function, which is called authenticate and launch. And authenticate and launch might or might not call the top function, which is called launch missiles, which just prints launching X missiles. So the program is a kind of a play on the War Games movie. So for anyone who's seen it, it's a little bit of fun. So if you try to compile this, unfortunately, you get a few hints that this probably is not a function you want to use. To the point where the gets function is dangerous and should not be used. It's hard to get more explicit than that. But you know what? We're just going to use it anyway. So when you run the program, so this is how it's supposed to work. It will print out this War Games missile launcher, and then you'll have to put in your secret. And so we're going to put in David as the secret, and then we get access denied and operation complete. So if you put in the wrong secret, then you get access denied. The right secret is Joshua, and this is from the movie, so if you saw the movie, it makes sense. Then you get access granted, and it launches 2 missiles. So this is how the program is supposed to work. So going back to this idea of a mental model, you have a secret, and then you put in David, you get access denied, and then operation complete, and you're finished. Or if you type in Joshua, you get access granted, launching missiles, and then operation complete. So this is sort of like, you can imagine the mental model of the programmer making this program. This is what it's supposed to do. So now we want to trigger some weird state. And so we're going to, because the thing is that the stack allocated buffer to take the secret is only 8 characters long. So let's just try to put in a much longer string. And global thermonuclear war turns into buffer overflow detected, launch terminated. Aborted core dumped, which is very unfortunate because, you know, we actually wanted to do like some exploitation with our fancy string here, so that it didn't work. But we did achieve an unstable weird state, which caused our program to crash. So that's good. So if we take that into this diagram, you type in global thermonuclear war, then suddenly we're in a weird state. Instead of getting to access denied, we ended up doing something else, which caused the program to terminate. Okay, so the reason why we got this error was because we had forward-defined protection on in libc, but you can turn that off like this. And it's even in CMake, and pretty modern CMake too, so it must be good, right? And if you do that, then you can try to run it again. And then you get stack smashing detected. So now it's a different error than before, but still not really helping us because it's still a problem. And the reason we're having issues now is because there's a stack canary. So this is a representation of a small part of the stack. A little bit simplified, but the idea here is that you have this stack-based array at the bottom, then you have this stack canary, and then you have some kind of return address. Because in old school stack smashing, stack buffer overflows, the idea was to overwrite the end of an array, and then overwrite the return address, and by doing that, being able to execute code inside of this buffer that you just overwrote. But what you see is that the stack canary is between the buffer and the return address. And so stack canaries was introduced as a compiler mitigation, where the compiler will insert some little magic code there. And before it does the ret instruction, it will check that the stack canary is still intact. And if it's not intact, it will abort and do stack smashing detected like we saw earlier. So you have the stack canary there. Another thing that is important to know is for x86 at least, the stack grows towards lower addresses. But of course, writes, like if you increment a pointer, they go to higher addresses. So when you write an array, a stack-based array, you're actually writing down the stack. So you're starting at the top and writing down the stack. And so that's how you get this behavior when you do the overflow over the end. But we can turn off stack canaries. So let's do that and see what happens. So we're trying it again. Now we get a segmentation fault core dumped. So that's unfortunate. So we have to go and check on Godbolt at least once in a presentation. But what you see is that in debug, these two stack variables here are on the stack. And they are also initialized. The end missiles is the number of missiles, and the allow access is initialized to false. And these are the ones that are going to decide how many missiles or whether or not we should launch the missiles. And so when we are overwriting the response buffer, we're hoping to maybe be able to overwrite these two stack variables. But nothing seemed to happen. And that is because we were running in release. And in release, these are optimized out. End missiles is inline because it's hard-coded to 2 and is never changed. And allow access with a little bit of a transformation is also unnecessary to have. And so both of them in release are gone from the stack. And so there's nothing to overwrite on the stack anymore. But let's try the debug build then. Let's see if we can get something to work. And so in debug, if we type global thermonuclear war, we actually get access granted, launching a couple of missiles. Then we get access denied, which is weird because this was a bool, so it's both true and false. Then operation complete. And it's looking okay, but the bools are looking weird. But it at least launched the missiles, which was what we were going for, right? But then I keep on saying to people, prefer C++ to C, so let's do this in C++ instead. And of course, how you do that is you change that one line, number 11, to C in. And then you just change it to a CPP, and then it's C++, right? That's how we do this. So now we go back, and we're going to compile our new C++ code, and we take away, we don't have any of the other exceptions that we did for C. So it's just this one line to compile our C++ code. And the stack canaries are back, so everything's back again. We compile it. And there was not even a warning. So this must be better than gets, because there was nothing to indicate that this was problematic. And so we just run it to make sure it works as intended, and it looks good. Okay, so then we try the release build, and we do the same we did before. We're passing in the global thermonuclear war, and we get a segmentation fault core dumped, which is unfortunate, and the same problem we had with the C code. Okay, but at least we know that something happened, right? Okay, so we tried the debug, and access granted, launches a bajillion missiles, and then segmentation fault core dumped. So that's interesting. We are having exact same issues with CIN that we had with gets, but now with no warning and nothing to say that this was a problematic code. But what we see here is that both end missiles and allow access are overwritten. So something in this string, global thermonuclear war, is able to change the values of these two stack variables. And so can we control them without crashing? Maybe. So end missiles is hard-coded to 2. Allow access is set to false by default. And they're right here. So if we have the stack allocated array, that is 8 bytes, and then we have these two variables, maybe if we just have a little bit of a longer string than our character buffer, then maybe we're able to overwrite those. Okay, so we're going to try to be very lead hackers. Hackers have a tendency to love having lots of capital A's. For some reason, it's like a tradition. I think it should have gone with capital B's, because capital B's are 42 in hex, and that's a better number. But anyway, but if you try this, it says access granted, launching 42 missiles, which is the best number, operation complete, and no crash. Okay, so this looks promising, but why 42? 42 is because end missiles is now 42. 42 in hex is 2A, and 2A is the ASCII code for star. So the star is controlling end missiles. But what is, well, first, let's see if we can set it to another number. So let's set it to D, launching 100 missiles. And 100 is 64 in hex, which is the ASCII code for D. So now we know we can just change the character right there, and we can control the number of missiles. But we also want to control, explicitly allow access, and so we guess that it's this 0 there will turn it off. So that looks promising, access denied. And setting it to 1, or basically anything else, will work. So now, by passing in a string that is only 2 bytes longer, we are able to control these two variables, which is awesome. But if you're going to be a lead hacker, you have to automate. The thing is, if you have to be a real lead hacker, they usually use Python, and I wrote it in C, so I don't think I'm a lead hacker. But basically here we have a struct, and we're going to just set the values that we want. So we want allow access to be true and then missiles to be 42, and then we just serialize that to standard out. And that means that we can do things that looks a little bit cooler, like this. We can pipe it in. So it looks fancier. So we test it with the C program, and we get access granted, launching 42 missiles, operation complete. And we can try it with the CPPP program, same exact exploit code, and it works there too. So now we have an exploit that works with both C++ and C. Awesome. Okay, so now we have to fix the C++ code. And one way that you can do that is you can set width on cin. And you do that with this std : set w max. But if we do that, unfortunately, our code stops working. So that's too bad. So now to fix what was fixed, to make it broken again, we can use sed to binary patch our binary. So let's do that to make it broken again. So what you see when you're using object dump, you can see that the hard coding of end missiles to 2 and allow access to false is just basically 2 bytes in the binary. Okay, so if we change those 2 bytes to true and 42, which are the right answers, then no matter what you pass in as your secret, you always get 42 missiles. This is why you sign your binaries. And check the signature. Okay, so, but let's try to look at a stack buffer exploit. So the idea, this is old school. This is, late 90s, early 2000s. This was the state of the art. The funny thing is, this still happens today, but usually in embedded devices. So you have, So you have the vulnerable, you have the target process, and it has the vulnerable program inside. This is Linux model. So in Linux, you start a process, and then you load the program into the running process. And so what we're going to do is we're going to use execve to load our shellcode instead, and replace the vulnerable program with binsh in the same process. So this is the goal for the rest of the talk. So the reason why it's called shellcode is because it traditionally gives you shell. So that means there's some kind of pound signal. So basically, it gives you a shell prompt. But back to the stack, again. The stack grows to lower addresses. The writes go to higher addresses. So when we write our payload, which is going to be what we're going to write into our array, this is sort of how we're going to do it today. So we're going to have our shellcode in the beginning of our array. Then we're going to have some no-ops in the middle. And then we're going to, at the end, we're going to overwrite the return address. Normally, this, like in a more realistic scenario, you would probably have a lot of no-ops in the beginning and the shellcode sort of in the middle, and that makes it easier to be a little bit more imprecise in jumping into your array. Because then if you hit a no-op, you can just kind of just no-op your way to your shellcode, and that's called nop sled. We're making it a little bit simpler this time. So we have to overwrite the return where the return address is with the address of the beginning of our buffer, because we want to be able to jump there and start executing the code that is inside of our buffer. So this is the goal. It's also important to realize that, of course, the instructions also go the same way, right? So the instructions will start here and go to higher addresses, which is also important to make this work. Okay, so we're going to have, this is going to be the framework for several of our exploits, so we're just going to go through it. So it's C again. So in the beginning here, we're going to put the shellcode in this string up there. Then we're going to take out the size. And then we need some kind of offset. And this offset here is going to be the how far into the buffer is where we have to write the return address so that when we overflow, we hit the return address on the stack. So we need to figure out how far that is. And then we have the padding in between. This is really fancy C code here, made to look simple on a slide. And we write out the no-ops in between, and then we have to figure out what is the address that we want to write, because the address should be the beginning of the shellcode. And then we write all of this as we go out to standard out. And this is to do the fancy piping thing that we did before. Okay, so the biggest important parts that we need to know the offset of the return address from the beginning of this buffer on the stack. We also need to know what is the address of the buffer in memory. So to cheat a little bit, we're going to make the buffer a little bit bigger, and we're going to cheat and actually output the address. And this is just to make it faster to do in the talk. So the problem here, one of the first problems we're going to see is that address space layout randomization is getting in our way. That is a feature that came in most operating systems, which will allocate the stack and other parts of memory, all sorts of parts of memory at different locations in memory. And this means that if you can manage to, through one run, figure out where things are in memory, in the next run, they will be in a different place. It used to be in the good old days that everything would be loading at the same address over and over again, and so this was much easier. But the great thing is you can turn that off. And so you have to be root to do this, but you can turn off address space layout randomization on Linux, and then this is all so much easier again. Again, something you might actually find on Stack Overflow, sorry. Although in this case, that was a better name. Okay, anyway. But to find the offset of the return address, we're going to use two small scripts which are in something called the Metasploit framework. Now, Metasploit is massive, and these are two very small things, but very useful for this. And so we are going to use pattern create to create a string of unrepeated characters. So it's a very, you'll see what it looks like, but it's a pattern that you can write into the buffer, and then afterwards we can use pattern offset to try to figure out how big of an offset in that pattern you are at. I'll show you. Okay, so first we're going to use pattern create, and we want a length of 150 characters. And so this is what it looks like. It's not very random, but it is repetitive. And so then we compile our program and put it in GDB. And put a breakpoint just before the return address, because what we're going to do is we're going to overflow the buffer with this string, and right before the return goes, we want to check what are the bytes that are on top of the stack right now. What did we manage to write on the return address? And if we can find the offset of that in our string, we know how far we have to write to hit that point in the stack. And so we just run it, and then put in our string. Doesn't really matter what happens now. It launches lots of missiles. But we hit our breakpoint. Then we can look at what is on top of the stack. And then we use pattern offset to figure out how far into the string that is. So that's at 136. OK, awesome. So since we cheated and we printed out the address of the memory, it's actually right there. And then the return address of the buffer is at offset 136, and so we can put that into our framework from before. But we still need shellcode. So in my talk at CPPCon last year, I went through making this. So I'm not going to go through it now, but we're going to do something similar later. So I think the most natural thing would be to test this shellcode first. So first just try to run the test code. Like if you see here, it has this little main at the bottom here, which basically executes this character buffer up there and then returns 0. And this is a standard way of testing. So if you Google shellcode for Linux, they often have this format, some kind of character buffer and then this little main to test it. And so if you run it, it says that it's 37 bytes long and it gives you shell. So you know, okay, so executing this character buffer will give you a shell prompt. So it works. But when we try to put it into the framework and use it, and we're going to use it in GDB because it's easier. And if you use it in GDB, then writing it out to a file and then reading it in GDB is nice. But when you do that, it doesn't really do anything. It kind of just hangs here. And when you debug it a little bit, when you debug it a little bit, the problem was that the string wasn't terminated. The bin sh wasn't string terminated, and so it just kind of reads and reads. Okay, so we need to be able to terminate the string. And so in this case, we're going to do that manually. So we're basically just writing the bytes. And if you look up there, this is the hex values, and then writing it in ASCII. And if you read it backwards, you say it's bin//sh. Awesome that it fits in 8 bytes. It's very useful. Anyway, but then we XOR RAX first, and then we push RAX, and then we push this string, and so now we have a null termination of the string, and we do that inside of the shellcode. And the rest of it is pretty similar to before. Okay, so we'll try that, and we just run it, and it works. Okay, so then we try to put it into our framework. And looks all rightish. But the problem is it says launching new program /bin dash, which is bin/sh symlinks to bin dash. But then it just kind of exits, and we never get the shell prompt. So that's unfortunate. So it sort of worked, but it didn't really, because we didn't actually get a shell prompt. So we have to go and debug this. So we can look at strace and try to see what is going on. And if you look at the strace log, let's see, then we're getting some kind of TTY errors. And so then we Google. A lot, because that's what you do when you get errors, even when you're an exploit developer. And you get this idea that the problem is because we have a shell already, we're running in a shell, so TTY is already bound into the process, and everything kind of got messed up. So what we're going to try to do is to close standard in and then reopen TTY and see if that works. But this is a little bit more complicated, so we're going to follow the same process that we did for a CPPCon. We write the C code for our shellcode first. We compile it. We use that as a starting point to write inline assembly and try to eliminate 0 bytes because we're using string functions to read this in. So we don't want like a 0 byte in the middle of our shellcode because these string functions are going to stop reading if they hit a 0 byte, so we can't have that. And then we put all of the bytes in a character buffer and then somehow execute it to make sure it works. So we start with writing the shellcode. The C code. And C code is very simple, right? We just close the file descriptor 0, then we open TT2Y, and then we just do what we normally would do to do the execve. Okay. And when we compile it, we build it statically because we want to make sure we have all of the code here because we actually want to look at it. And we turn off stack canaries because you don't really need stack canaries inside of your shellcode because it's just noise. And then we just make sure that there's actually no dependencies. And we run it and it works. Okay, so we know it works, the code itself. so then we start looking at the assembly. And so what we see is that this is what it turns into. So these, so the close is underscore underscore close. The open is underscore underscore libc open, and then execve. So if we go and we look at the calling convention for x86 64-bit Linux, we have to figure out how are the arguments to the system calls actually passed. And close is very simple. It only takes an unsigned int, so it's quite simple. But the other ones are kind of complicated, like OpenNet takes a whole bunch of arguments passed in different registers. So we have to emulate this to be able to do these system calls. So the best way is just to go and look at the assembly of our compiled program and then use that as inspiration to write our own inline assembly. So here we have for close, we see that it moves 3 in hex into EAX, well, 3 into EAX, and then calls syscall. So then we just tried to emulate that. Because we had to put 0 in RDI, so we just XOR RDI. And the reason why we're using XOR to zero out things is because then we don't get any 0 bytes. So it's a simple, but there are many different techniques for not having 0 bytes, but XOR doesn't give you any 0 bytes in the resulting code. And then we zero out RAX, and then we write 3 to AL. And the reason why we're using AL here is also to avoid any 0 bytes. So then we look at OpenNet, and here we have, so the syscall number down here loaded into EAX and then syscall. But there's like a whole lot of other code, and we wanted to make it as simple as possible, and this had like lots of logic. So we're trying to get away with as little as possible. So we kind of used the trick that we did from before. We need to load this string, this dev t2y. And so we do the same we did before. We push RAX, and then we write the string, which also this time fits in 8 bytes, which was very convenient. And we push that on the stack, and we use that as the file name. And then we just try to zero out all of the other registers and hope it's OK. And looking at execve, we can basically use the code that we had before. So we don't really have to worry about that. And when we run it, we put it all together in a character buffer, and we run it. Or no, yeah, inline. And we put all this inline assembly and into a C file, and we run it. It works. Okay, so that means the assembly is okay. So we have the assembly instructions. But when we look at that when we compile it, we see that we have a problem. Because we have some 0 bytes right here, because we have a move into EAX. And we can't have that. We were previously moving into AL, which gives you instructions with no 0 bytes. But the moment you're starting to move into EAX, we're getting 2 0 bytes right there. So how do we fix that? Well, it's this line that's causing us trouble right here. So keep it simple. Just load 255 and then just increment it twice. And then we're back again, and we have no 0 bytes. It's not great code, but it wasn't supposed to be great code either, so it doesn't really matter. Anyway, so you will find, so this is this is the assembly, and these are our bytes for close, and for open, and for execve. And so putting it into a character array, so you have close, open, and execve. And then we run it like we did before, just to test it, to make sure that the character buffer, when you execute it, it works. And of course, here we have to run it with XX stack, because we want to execute it on the stack, of course. We did that with the other ones as well. I just didn't point it out. And it works. OK, so we have a character buffer, which works. Now we have to test it inside of our exploit. OK, so we do the same we did before in GDB. So we write our exploit to a file, and then we can read it in GDB. And we're going to try to debug it to see that it actually does what we wanted. And so it says executing new program / bin dash. So that's a good sign. And we get a shell prompt. So it worked. So that's awesome. Yay. Okay, but that was in GDB, and we still need it to actually work outside of GDB. So let's do it with the program standalone, and that works too. So now we have an exploit. If we pipe it to the program, it can overwrite and actually do execute inside of the process. So it's a double win. But we cheated, like tons of times. Throughout all of this presentation, we've done like turn this off, do this thing, do that. And the big things is we turned off address-based layout randomization. Because that is actually kind of annoying. But it isn't as much of a mitigation as a lot of people want it to be. Because what you see today with modern exploit development is these applications are long-running applications. So if you are able to leak addresses in memory, you can deduce the memory layout. For us, it's a little bit of annoying because we have a very short-running program and basically just does one thing and exits. But if it was running in a loop over time, I might be able to fish out addresses and figure out where things are in memory, and use those addresses again for newer things. And that's what you see. So information leaks, they call that. And they use information leaks to defeat ASLR and be able to continue. We made the stack executable. That is weird. Today, currently in all modern operating systems, the stacks are not executable. They are non-executable pages in memory. But there are also a lot of exploits that when they actually manage to execute a little bit in memory someplace else, they actually make the stack executable, remap it as executable pages, and then just do a regular stack smashing. So that is also defeated by many exploit developers today. We turned off stack canaries. Stack canaries are hard to defeat, and also probably the reason why stack buffer overflows are not very common anymore. And we printed the address of the buffer instead of like having some kind of information leak. So what are newer exploitation techniques? What are the kids using these days? Actually, there was a section of time a few years ago. You had information leaks are very much used today, but you had return-oriented programming was very popular. It's not as popular anymore, but return-oriented programming was basically to try to defeat this non-executable stack problem. Because you can still do your buffer overflow, but you can't jump into the buffer that you have and start executing there because this is not executable memory. So to get past that, instead, they did variants of something they used to call return to libc, which was basically, instead of executing the code I have here, jump into libc and execute functions there. So instead of writing the address of something inside of your own buffer, you're writing the address of something in a library that is already loaded into memory. Now, a variant of that became popular where you would just write different addresses to any place in memory, and even in the middle of an instruction. And you had Python programs that could basically, you could take the binary as an input and actually produce all of the addresses you needed to jump around. So you would write these addresses to the stack, and then you would return constantly, and by using these returns in these little gadgets, it would return to the stack, pick a new address, jump there, execute a little bit of code till it got to a return, go back to the stack. The return would pop an address off the stack. And so you basically program by writing all of these return addresses on the stack instead, inside of your buffer. So it was very popular to be able to still be able to execute code even though the stack was not executable. So coming back to this diagram though, this weird machine. So the mental model that the programmer has of the program is the mental model of a healthy program, a program that has not been exploited or has any vulnerabilities. But we all know that our programs do have bugs, right? And one of the things that you see is exploit developers will use fuzzing techniques, where they will fuzz this on all sorts of surfaces of area where you're reading things into memory. And the fuzzers are looking for crashes. And the reason why the fuzzers are looking for crashes is because crashes are a sign of a weird state. Weird states are unstable. Weird state usually crash. So if I can inject things into this process, causing it to crash, that means there is a path from the input to something in this program that can cause a weird state to happen. And if you can then provoke this weird state, because these fuzzers will keep the input that actually caused this program to crash, so you can reproduce it. Then you try to use that. Like we did in the beginning, we had this global thermonuclear war, which is just a random string. But after a while, we managed to finely tune the string a little bit, and so we could actually use it to control the stack variables. And in the stack buffer overflow, we used it to do the stack buffer overflow exploit. So the idea is to try to figure out some kind of input that you can feed into this program, either through a file or environment variables or network traffic or input in some way, that can actually trigger this weird state. And then you spend a lot of time trying to stabilize this very unstable state and then try to direct it to do the things that you want. And having these things and having them being pretty stable has given them a name. So they call them primitives. And so they have primitives, and they have they have like special classes for them. So you would say, for example, I have arbitrary write primitive. That means I have a way of making this program write something somewhere. So you have some weird state that you can stabilize enough that you can get to a code path that will write what you want a certain place in memory. Then you could have an arbitrary read, where you are able to feed some kind of information to make it possible for you to read information, and things like that. And so these sort of become like functions that you implement by trying to stabilize and control weird states. And then hopefully in the end be able to execute the code that you actually wanted to run. So programs that we write, they need to be deterministically correct, or that's a goal. Generally, we want them to be deterministically correct. But exploits only need to be probabilistically correct. And so when you look at these competitions for exploit development, they will generally run their exploits thousands and thousands of times in a loop. They have to keep the target program stable while they do this, because they only have to hit once in 1,000 to be able to execute exactly what they want. So being able to keep it stable enough, and then they have generally time limits. So you have to be able to do it within 4 tries and within 30 seconds or something, and then but you can run as much as you want within that time. So exploit development is programming. It's just a very strange and kind of unfriendly machine. And that's my talk. Thank you. So we have some time for questions. Any questions? Everybody's really tired? Okay, well, thank you so much for coming.